Hi, Dave Allwell. This is Lab 7. My voice is not completely recovered from my cold, so I might be a little difficult to understand. I'm going to try and move through this quickly so I can save my voice for class later today. On the left-hand side of the screen, you should be able to see the lab sheet for Lab 7. Two simple objectives today: show you how to do an analysis of accelerated life data in ALTA, and also how to simulate a test plan. While you can do some accelerated life test analysis in Minitab, it's not as robust as ALTA, so I've decided that I'm only going to show you how to do this in ALTA today. Let's begin. To begin, we need to first open an ALTA worksheet. So from our window, we'll go to Programs, LiveSoft, ALTA 8, and it opens for us as you see in the screen here. Then I have to open a repository. I'm going to create a new repository by selecting the file, New Repository. I'm going to call this one Lab 7 Demo 2. I already have a Demo 1 because I've practiced this. I know you won't believe it that I practiced this, but I have practiced this already. And I'll go ahead and click on Open. When I do that, it asks me what type of a folio I want to open. So I'm going to scroll down and pick an ALTA standard folio. Okay, and then I get something that looks like this. So that's where I wanted to be. Now we have some data to enter. I've already entered this, so I'm going to pause and reopen the spreadsheet, the folio that has this, and come back in a moment. So I've opened the folio where I previously entered the data. I now want to choose to select a model. First thing I'm going to do is set the use stress to, pardon me for a moment, set the use stress to 293 Kelvin. Remember, to switch from Celsius to Kelvin, you have to add 273 to the Celsius score. So 20 Celsius is about 70 degrees Fahrenheit, and that's what I'm going to set my usual stress level to be, about office temperature. Then I've got a choice of models I can select. The first three are the three life stress models that I discussed in the classroom. There's a couple others that we also talked about. I'm going to do an Arrhenius, and the software allows me to pick one of three distributions. I'm going to pick Arrhenius Weibull here. I generated this data using the Monte Carlo feature, which I'll show briefly at the end, so I know that this is the distribution from which it's generated. Because it's a small data set, that doesn't mean it'll be the best fitting distribution, but it should be reasonably plausible. So I select that, and then to actually do the calculations, I just need to hit the calculate button. Okay, and then that fits a model for me here. Okay, once I have a model fit, then I'm able to do the same sort of calculations I did in Weibull. The difference being I have to say what the stress level is every time I want to do a calculation. So for example, to find the mean life, I selected the quick calculation pad. I select on mean life, I say my usual stress is 293. I have my lower one-sided confidence bound at 90% already figured, and I select calculate, and I see that at the usual stress, my best guess is 13,600 hours for the mean life, but there's a 10% chance it could be as low as 3,200 hours roughly. Just by chance. To find the time by which the first 1% failed, that's my B 1%, again with the 90% confidence level. And I think the time by which 1% of my items fail is estimated to be 2,117 hours, but there's a 10% chance it could be as low as 590 hours. Similarly, to find my reliability at 293 Kelvin and emission time of 5,000 hours, I can calculate that, and I get that it's 92.8% is my estimated reliability, but there's a 10% chance it could be as low as 21%. And again, the reason these two numbers are wide is that I have a relatively small data set, and I'm going to have an awful lot of uncertainty in my estimates. There's several plots I can get that I'd like to demonstrate. First, I'd like to demonstrate by clicking the plot window here that first plot I want to demonstrate is my use level probability plot, and that's what the data looks like when every point is extrapolated down to the use level stress, which in this case is 293 Kelvin. Not a great plot, but again, with a small sample size, there's lots of uncertainty, and you wouldn't necessarily say reject it based on that. Pause again for a moment. This plot is not too particularly interesting, although if I add a confidence bound, one-sided top confidence bound on reliability, I can see how much uncertainty I have. For example, my estimated reliability at, let's just change this here to make this a 0.1. At 1,000 hours is estimated to be 0.2%, but it could be as high as 1, 2, 3.5%, which is a factor of 30 times greater. Okay, so again, a lot of uncertainty here, especially as I extrapolate for lower life. A more useful plot is this probability plot with Weibull. Here, I'm going to turn the confidence bounds off at this point. This is a pretty good diagnostic plot. It shows the data points in their different colors at the different stress levels and the models that are fit through that. What this is useful for is trying to decide, one, does the data look to be roughly linear? Two, because there's a common slope assumed for each of these stress levels, do the slopes appear to be about the same? It's kind of hard to tell here with only 2 data points. It's not a smoking gun bat against the data. And the third thing is, are the spacing levels for the estimated slope lines look to be about right? In other words, does it go through the data? We fit a 2-parameter model for this life stress model, so having 3 stress levels allows me to get a sense of do the points line up appropriately, and here it doesn't look too bad. So I could add confidence intervals to that. It gets a little noisy. You saw how to do that. The third plot I'd like to show is the life versus stress plot. And let me just turn that off for a second and redraw. And so what this does is it shows what my probability density function and points look like, the various stress levels, and then takes the characteristic life, which remembers the time by which 63.2% of the units fail, and shows how that goes up as my stress levels drop. So in particular, my life down here is about 600 hours, 559. But when I get up to my usual use conditions around 293, then it's up to almost 15,000 hours. Okay, so it gives me a sense for how much acceleration I get as I increase my stress level or decrease my stress level. And again, that's a useful plot. That can also have confidence balance put on it. I'm going to stop here for a moment. I'd now like to show how you can simulate a test plan and get an idea for how much uncertainty is going to be from a given sample size. To do this, I'm going to go to the Insert menu and go to my Alta Simulmatic utility and click here. This opens up and gives me a table where I can put the number of points, the various stress levels, and the various types of a distribution. I may not know what B and C are supposed to be for this Arrhenius model, or for the other combinations I might have here. So there's this quick parameter estimator that allows me to do that. So in particular, if I say I know that my shape parameter is going to be, let's say 2.6, and that my median life is going to be 2,000 hours at the usual use stress, which I'm going to put in here as 293. Then I can go to the next screen and say if that's what my characteristic life is at the 293, I can pick another value for the life, the stress value. Here I'm going to pick, I believe, 373. And I'm going to say my characteristic life at 373 is 50. Okay, so it's drops by a factor of about 40 when the temperature goes up 80 degrees Celsius. Okay, so I click on that and go next, and then it gives me what the corresponding parameters are for B and C that match the life stress model that I fit. So if you click update, it loads those back into the sheet here. Then I go through and put the various levels at. So I'm going to put 50 points each of 4 times. And I'm going to use the sum at the usual stress level, 293. Then I'm going to have at 323, 343, and 363. Okay, so it's going to generate 50 points at each of these stress levels and this model, and randomly generate what the times to failures are. Again, say that my stress level is 293. I'm going to put, I want to show some of the censoring time here. So I'm going to say that the data is going to be censored after 250 hours. Don't want it to get too far ahead. And then I'm not going to do 1,000 data sets, I'm going to do 100 data sets. The reason I like 100 data sets is it allows me to count down 10 and get fairly easily and calculate what the 90% confidence intervals would be on either side. For the analysis, a 90% confidence interval, I'm going to leave this alone. I'm going to leave this alone, although I could put different reliability values or different times in there to get various things estimated from. So now I'm going to click OK, generate. And what happens is it generates 100 times data sets with those characteristics. It fits the parameters each time for each of those data sets. And that's sorts the data by the lowest to highest. I'm not really too interested in that. What I'm really interested in is the plot that I get. So when I collect a plot here, and I've got some extra room over here, so I drop a couple zeros off. 1, 2, 3, I'm going to drop 4 zeros off. I'm going to add 2 zeros here. 100 to 10,000, that's what I want, sorry. Okay, and redraw that. So it gives me a sense for, with that particular data set, how much uncertainty I'm going to have. Here's my true parameter, true model in the green, and for each of the times I estimated, that's how much variability I got. So in particular, for estimating my life at 1,000 hours, I could see that it could be as 1, 2, 3, could be as low as 4%, or maybe as high as 20% unreliability at 1,000 hours. Yeah, okay, so I get a sense for that particular design and that number of data points, how much uncertainty I'm going to have. Well, what I want to do is go back and try this again, but now I want to make it be just 10 points each time. Okay, so everything's the same except I've cut the number of data points way down by a factor of 5. I generate this again, I get a new plot, and now when I look at the graph, and again I change this to go between 100 and 10,000. I see that I have a lot more uncertainty, an awful lot more uncertainty. In fact, at 1,000 hours, it goes between 0.15% to 20, 30, 40, 50, 60, 70, 70%. So what it makes the point, which I've tried to make in the slides, which is that when I have a lot of uncertainty, I'm sorry, small data sets and extrapolation, I get an awful lot of uncertainty, and this is a graphical way to demonstrate it. It's useful when you're looking at somebody's proposing an accelerated life test when you want to say, okay, so that's your plan, let's just see how much precision we'll have for it. You can load it in and simulate that particular test plan for some reasonable values of what you expect, and come back and say, is that going to be enough precision for us to answer the mail or not? And then you can trade test resources against precision, which is always the hard part when you're doing this. There's a couple other features I want to show here. If I go to my insert menu here at this Alta test plan, one of the things I can do is put in for some various types of test plans. I happen to like this 421 allocation plan. I can put in some parameters and some assumptions about what my distribution is, some assumptions about what my life stress relationship is, and some assumptions about what my probability of failures are at different times and stresses. This is not really important, but what is important is it will tell you what your various stress levels ought to be to test your data, and what percentage of the units ought to be at each different stress level. And that's handy. And then if I want to get a certain amount of precision, if I want the ratio of my lower to upper, my lower percentage confidence level to the upper confidence level to be a ratio of 3 to 1, it'll tell me what the sample sizes I need to put on to do that. And then I would take, for example, 20%, 20 numbers, and 57% would be at this level or whatever. This gets to be much more useful when I put realistic numbers in. If I'm starting off and saying I don't have any idea of how big of a sample size I should put. Now what usually happens, so I've set this at an available test time of 100, that's how much test time, and at 100 I'd be lucky to see 1% of my units failing. I set up my maximum stress level is going to be 400. There I might see 75% of units failing, for example. So when I put more reasonable probabilities here for what the fractions failing are going to be at these various stress levels, and then generate the test plan, I get different allocations and different stress levels. These are more reasonable stress levels. And when I get my sample size here, I get a much bigger sample size to get the amount of precision I wanted. So this is a tool which we're not going to talk about, but I'm just letting you know it's there for helping me understand or get some insights on how to develop an accelerated life test plan. Similarly, if I can go to insert a project. Let's see, I'm looking for my particular view test plan. Oh, I'm sorry. If I go over to a tools, let me pause for a second. I was looking for something, couldn't find it. If I go over to the Home tab, I've got this Alta Monte Carlo tool set. And what this does is allows me to simulate a particular model. So if I put this 2.6 here, I can use my quick parameter estimator to get these parameters again. As I did before, 2.6, 293 is my stress level. I like 293, you probably figured that out. I could say what my characteristic life's going to be at 363. Again, we'll say that was 40. And then update these particular parameters, and then I can say I want 25 points at 325 Kelvin and 25 points at 350 Kelvin and 25 points at 375 Kelvin, just to make something up. and it will generate that data set for me. Okay, and this, I did something like this to actually generate the data that we used. I can also, when I'm back here doing this, set up a censoring scheme to say censor it after 250 hours or 500 hours or whatever. And again, set what the usual stress level is at 293 here again. I can pick my random number seeds here if I want to use something different. So this one with the censoring comes in and generates the data for me. And I see I have all these different censor times. Again, by clicking on this funnel, I can group the data, group it, and then change it to a data sheet. And then all my suspensions are clustered together. It makes life a little bit easier for me when I'm trying to enter it. Okay, so those are things I wanted to show. Yep. This accelerated life testing is half of a full course that I teach as an elective, so you're just getting a little taste of it here. But again, as part of this survey, I want to make you familiar with it. I also want to give you the tools to solve some simple problems. Most importantly, to make you a good consumer of somebody else's product. When somebody else comes in and said, I did this accelerated life test, you know enough to look at what the pitfalls are and ask the right questions, to look for the right graphs, and you can do a little what if with these tools to simulate the models that are produced and see if you believe the amount of precision that people are telling you comes from it. So I hope you find this helpful. I will see you later today.